Hello, my name is Faisal Ahmed and today our topic is branching tubes. So, biofluid mechanics of branching tubes refers to the study of fluid flow such as blood, air or lymph through branching tube networks in biological system. This field combines principle of fluid mechanics with biology to understand and optimize the behavior of fluid in these complex systems. There are some key principles in biofluid mechanics of branching tubes. First, flow types. Laminar flow, common in smaller branches like capillaries, bronchioles, where fluid flows smoothly in parallel layers. Turbulent flow occurs in larger tubes, example aorta, trachea, where high velocities create chaotic flow. Second type is continuity equation. The principle of conservation of mass ensures that the total flow rate, which is volume per unit time entering a branching system, equals the flow rate leaving it. Q parent is equal to sum of Q branches. First, pressure and resistance. Pressure drops occur as fluid moves through the branching system due to viscous resistance and bifurcations, governed by Paul's law for laminar flow. R is equal to 8 microliter upon pi r की power 4. First, Murat's law describes the optimal relationship between the radii of a parent tube and its branches to minimize energy expenditure. Examples in biological system. First, cardiovascular system. Arteries and veins. Arteries and veins. Blood flows through a network of arteries, arterioles, capillaries, venules and veins. Pressure gradient drive blood flow with the highest pressure in arteries and the lowest in veins. Optimization of branch diameter reduces energy loss. Second, respiratory system. Bronchial tree. Air flows from the trachea into the progressively smaller bronchioles ending in alveoli for gas exchange. Branching increasing the total cross-sectional area, reducing air velocity and resistance. Third, lymphatic system. Lymph is transported through branching lymphatic vessels, collecting interstitial fluid and returning it to the circulatory system. Fourth, plant vascular system. Branching xylem and phloem tubes distribute water, nutrients and sugar efficiently across a plant. So there are some key biofluid mechanics parameters. First, Reynolds number Re determines where flow is laminar. Reynolds number is less than 2000 or turbulent. Reynolds number is greater than 4000. There are subcomponents. The ability of tube walls, example blood vessels, to expand and contract with pressure changes impact flow dynamics. Some applications of biofluid mechanics in branching tubes. First, medical diagnosis and treatment, predicting blood flow in cardiovascular disease, designing stents and vascular graft with optimal flow dynamics. Second, tissue engineering, creating artificial branching networks for organs or implants, example bioengineered lungs. Third, drug delivery, optimizing branching networks in microfluidic devices for targeted drug delivery. Fourth, understanding pathologies, studying abnormal flows like aneurysms, atherosclerosis caused by altered branching geometries or compliance. Some challenges in modeling branching tubes. First, complex geometry. Biological branching networks are often irregular and asymmetrical, complicating mathematical modeling. Second, non-Newtonian fluid. Many biofluids, example blood, exhibit non-Newtonian behavior where viscosity changes with shear rate. Third, dynamic nature. Tube properties, example compliance, radius and can change over time due to physiological or pathological condition. So, the study of biofluid mechanics in branching tubes provide insights into how biological systems achieve efficient fluid transport, and inform the design of biomedical devices and treatment. So our next topic is steady flow, Bernoulli's equation and continuity equation. In fluid mechanics, steady flow refers to a flow condition where fluid property like velocity, pressure, and density at a given point do not change over time. The Bernoulli's equation and the continuity equations are fundamental principles for analyzing such flows. First, Bernoulli's equation. Bernoulli's equation describes the conservation of energy in a steady, incompressible, and inviscid flow. It related pressure, kinetic energy, and potential energy of the fluid along a streamline. The formula is P plus half PV square plus PGH is equal to constant, where P is pressure, small p is fluid density, V is fluid velocity, G is acceleration due to gravity, H is height. Key insight from Bernoulli's equation: first, pressure velocity relation. If velocity increases, pressure decreases, and vice versa. This explains phenomena like lift in airplane wings for the Venturi effect. Second, height effect. An increase in height decreases pressure or velocity due to gravitational potential energy. Third, absorption. Inviscid or frictionless flow. Incompressible fluid applies along a streamline. Second is continuity equation. The continuity equation ensures the conservation of mass in a steady, incompressible flow. It states that the mass flow rate remains constant along a streamline. A1 V1 is equal to A2 V2, where A1 and A2 is cross-sectional area at point 1 and point 2. V1 and V2 fluid velocities at point 1 and 2. Some key insight from the continuity equation. First, area velocity relationship. If the cross-sectional area decreases, velocity increases, and vice versa. This explains why fluid accelerate in a constriction like in the throat of Venturi tubes. Conservation of mass ensures no mass is lost or gained as the fluid flows. Third, absorption, steady flow and incompressible fluid. Some applications in steady fluid. First, Venturi effect. A decrease in cross-sectional area leads to an increase in velocity and a decrease in pressure, which is combination of Bernoulli's and continuity principle. Second is pipe flow. In system with varying diameters, the continuity equation calculates velocity change while Bernoulli's equation predicts pressure changes. Third, flow in branching tubes. Continuity ensures the total flow rate entering equal the flow rate leaving, while Bernoulli's equation explains pressure and velocity distribution. Aerospace engineering. Bernoulli's principle is crucial in understanding lift on wings. Medical application used to analyze blood flow through arteries, example stenosis and aneurysm, and respiratory airflow in bronchi. Example, combining Bernoulli's and continuity equation. Scenario, a fluid flows through a horizontal pipe with varying diameter, given inlet area A1 and velocity V1 and pressure P1, outlet area A2, velocity V2 and pressure P2. Using continuity, as we know, A1 V1 is equal to A2 V2. And if we are using Bernoulli's equation, so as the formula we have to know P1 plus half small p V square is equal to P2 plus half small p V square. Both equations together provide a comprehensive understanding of fluid behavior in steady flow. So thank you. That's all for today.